Welcome back, everybody. We're going to keep going on our reactions of alkenes. We had regioselective, non-stereospecific reactions with hydrohalogenation reactions. We got almost an identical mechanism with hydration. What's hydration? Just like we take a sip of water when we are thirsty, alkenes can take a sip of water when they're thirsty. And so that's what we're going to see. How does the alkene drink up some water? Let's look at it. So obviously you got to have water in the reagent. And I'm going to do two different mechanisms here. One with sulfuric acid and the other with mercuric acetate, THF water. All right, so let's look at the first mechanism here. As I said before, it's almost identical to the hydrohalogenation. So if you haven't seen the hydrohalogenation video, guys, please watch that because it's got models and stuff like that. All right, let's go. So sulfuric acid is a molecule that can mix really well with H2O. It can give you HO3+, which is hydronium ions. And some books just protonate from here, or you could also protonate from the sulfuric acid because it's really very acidic. It has a very low pKa, very, very acidic. So your alkene comes in and sees this little proton here almost coming off of the molecule and grabs it. And we will have over here a molecule where the hydrogen prefers to go on what do I hear? A or B? Always to the carbon that has more hydrogens. You don't really even need to think about it. Just remember Markovnikov's rule. But if you want to think about it in such a way that you're making the more stable carbocation. So if the pi bond pops here and hydrogen goes here, your carbocation goes secondary. If it pops in the other way, your carbocation would go primary, which is a no-no. So now that you have this, and you'll have your HSO4 minus, and this is also quite acidic, and it is really not a good nucleophile because the oxygen is in resonance with all of this. So this is not a nucleophile. I'm going to write that down because a lot of people use that for a base or a nucleophile where in the presence of water. And if you look at the pKa values, that's really not what's going on. Okay, it's not a base and it's not a nucleophile compared to water. Water would be a better nucleophile compared to this. Now you're going to have water then attack, and since water is what you have all around you in the ocean, I'm going to use a blue for the water. It can come in and attack from the top, or it can attack from the bottom. It has a 50-50 chance of attacking from the bottom or top because it's a flat carbocation and therefore it's not stereospecific. So I'm going to just draw this out with a squiggly line which shows it can be up or down. And since you have 3 bonds to an oxygen, it's a positive charge, right? Now you can take off your hydrogen from the water with another water molecule. Again, as I said, water is a better base than your HSO4 minus. If you have any doubts, look at the pKa chart. Therefore, now you can have a hydroxyl that can be up or down, as I said. There's an equal opportunity for that attack on the plane above the carbocation and below the plane of the molecule. So this is going to be a 1-to-1. Therefore, it's non-stereospecific. It is regiospecific because we don't put the positive charge on the terminal carbon because primary carbocations are really, really bad. All right, so is that all? Is that the end of our story? Look at the numbers here. This entire thing is only 20%. So probably this is about 10% and this is about 10%. Where did the rest go? Look at this molecule. It's got a skeleton that's completely different from this. So there is a skeletal rearrangement. How does that happen? For a skeletal rearrangement to happen, carbons have to hop around. So that's what really has happened over here. This carbon is not here. And there is a carbon here on this carbon. Therefore, this carbon has hopped over to the next carbon. We saw that before in HX. We called it a methyl migration. So let's look at it. So here is one option. Or you can also have another option. And I'm going to draw that over here. You are going to take that secondary carbocation and you are going to rearrange it to a more stable form. So a methyl group, a carbon, rolls up its sleeping bag and moves over to the next tent over there, right there. So you have over here a positive, then here you left a hole behind, and the methyl goes over to the next carbon, and you have another methyl here next to it. And I'm just going to put the hydrogen here because that's the hydrogen that we use for protonating that alkene in the first step. Now that you've moved over here, this is really very stable because now it's a tertiary carbocation, and you know you can't really beat that. Yippee, it's really happy. This is a secondary. Secondary is not that hot. So here's a secondary rearranging to a tertiary, and that is a 1,2 methyl shift. We did do a transition state for that in the hydrohalogenation reaction. So, please look at that. This is a rearrangement. So whenever you have Markovnikov addition, always bear in mind, if you have a secondary, it will go to a tertiary. If you have a primary, which hardly forms, you would go to a secondary and if possible a tertiary. Always going towards the higher order carbocations, all right? More stable carbocations. All right, let's continue with this. Now that you have this over here, you could then attack this with water the same way you did before, above and below. In this case, does it really matter? No, because it's achiral. You're not going to get an R and S mix. Therefore, you're just going to get one product, and that is just by adding an OH2 across 3 carbons. This is your H that was over here, and this is the methyl that walked over to its new home on this carbon here. Now again, you don't want to be stuck in limbo with a positive charge in your molecule, and you would deprotonate with water, and that is going to be a OH and H, which makes H2O, which is water. That's why we call it a hydration. You're just hydrating the molecule. It's just getting a sip of water. So this is water addition. This is 4/5 of the product, which means most of it is going this way. Just a little bit is going this way. All right. So take-home lesson from this is whenever you have things that add a proton and create carbocations, there will be rearrangements to get to the most stable carbocation wherever and whenever possible. Well, let's say we don't really want this. We want this and this alone. How are we going to prevent this rearrangement? Well, you can prevent the rearrangement by adding mercuric acetate. Okay, so this process over here is pretty much the same reaction, and this is to prevent rearrangements. We're going to use this. Let's see how this works. Mercuric acetate is a very big molecule. So you have over here a mercury, and acetate is basically a methyl group with a carboxylate. So you're going to take this and use that to then react with an alkene. All right, so let's take our mercuric acetate and run with it. Where is it going to attack? Well, mercury here has got 2 acetate groups, and these tend to be electron withdrawing. Therefore, mercury is electron deficient, and therefore this is going to be your electrophile. And here's your nucleophile. And the storyline never changes throughout our entire organic chemistry reactions. Nucleophile, curvy arrow attacks the electrophile. The electron-rich shoots a Robin Hood arrow to the electron-poor and donates its electrons. All right. So let's go from there. Then you have a mercury that is then going to form a bond with both carbons. So therefore the mercury here, once it attacks, has electrons that would hook on to the other end, and an acetate is going to be dispelled. Why is that? Mainly because of the size. Mercury is a huge mama atom, and it's going to hold on to both ends. And here you are going to have an acetate then leave, and you are going to form this intermediate. So now you have your mercury acetate here. Your mercury acetate is not going to be floating around for too long in this form, mainly because it's a positive and you want to make it neutral. Well, what is there to attack? There's water in here, so let's bring it in. So your water molecule is going to come in. And there is a preference here to attack at the most substituted carbon. I mean, why is that? You might even think it might prefer this over this due to steric, but it does prefer this because look at the product, 94%. Okay, so it's predominantly attacking at this position compared to this. So it's mainly electronic reasons. I'm going to draw both of the possibilities just to show you why. So if it attacks at this carbon, you are going to have, let's say your water molecule like pours in its electron into this carbon, you are going to have this bond break over and form an incipient secondary carbocation. All right, so an incipient secondary carbocation is a lot more stable than this if it forms an carbocation here. So let's draw the other possibility for that so you know what I mean. So your molecule comes in. So here's your Ag, OAC. This is AC, acyl group. So the water molecule, let's say, came in over here. This, when it tears apart, is going to create an incipient positive on a less substituted carbon. Okay, therefore, a secondary incipient carbocation is more stable than a primary incipient carbocation. And why is that? Because as the carbocation forms, you have these carbons donating electrons into that orbital to lower the energy. Whereas over here, you have two hydrogens with a 1s, can't really give anything. So this is going to be your stable molecule. This is going to be your unstable intermediate. So this is stable and this is unstable. Therefore, almost all of the product is going to come from this intermediate. So now you have tertiary next to this, and there is no hope of any of these methyl groups migrating over here, mainly because both these positions are held by the mercury. So methyl migration does not take place. So that's very important, because the only reason you'll go through this messy toxic mercury pathway is to avoid rearrangements. That's the take home from this. Because if without the mercury, most of it would have rearranged. With the mercury, almost no rearrangement. Now that you've drawn this out, well, let's put the OH2 here. It makes a bond, kicks out the mercury to the next carbon, and the OAC is still hanging on there for dear life. And you would have this intermediate now. One more step to make it neutral, and that is just taking another water molecule and deprotonating that. So here's your water molecule that's floating around, that comes over here and deprotonates that. And I'm going to draw that on top as a hydroxyl, an OH. Your mercury is still hanging on there with one arm. Well, how do you get rid of it? We have to add sodium borohydride. It's not really very expensive, so we throw in some sodium borohydride. And this is a radical mechanism, so I'm not going to do a backside attack here. And we're not going to talk about the mechanism. That's going to replace the mercury with a hydrogen. And that is your final product here. It's just a hydrogen. And here is your OH. So overall, you took an alkene and added HOH, which is basically H2O, which is hydration. And this, again, you can have your mercury on top and have the water attack at the bottom, or you could have your mercury at the bottom and have the water attack on top. So you would get plus and minus. So I'm going to put a squiggly line here. You would get plus and minus, and there's equal probability for both of them. So that is going to be a 1-to-1 raceme. So this is not a stereospecific pathway. It is non-stereospecific, but it is regiospecific. Almost all of the hydroxyl is on this carbon, none on this. The unique thing about this mechanism is that there are no rearrangements. All right, so here are two ways of doing hydrations, one with rearrangements, one without rearrangements. In the reaction where you don't have anything to prevent a rearrangement, rearrangement would happen, and that would be your major product. Why does it rearrange? It's going from a less stable carbocation to a more stable carbocation, so it is reducing the energy of that pathway. Therefore, you're getting a predominantly high amount of a tertiary alcohol. In this method, we are taking mercuric acetate and blocking the top or the bottom face of your alkene. Therefore, the methyl cannot move over. You're preventing the rearrangement. Once you form your mercury, you can attack on the more substituted carbon. This is a non-stereospecific reaction. You will get your hydroxyl above and below in about equal amounts. So therefore it's non-stereospecific, but as you can see, it is very regiospecific here. So it's selecting a certain region over the other, which is pretty much the definition of regioselectivity. So I hope it kind of brings home some of the mechanisms that you saw earlier, and just want to let you know, if you have any questions, don't hesitate to ask me. I will talk to you soon, guys. Bye.